Welcome to Shelly Physics episode on electric field calculations. This is part 3. We're looking at a surface of charge. I'm going to use that problem solving method for electric field calculations we learned about in the last episode, in part 2. So in this particular one, imagine a big disk here. You can call it a sheet. And I've got a circular sheet. It just helps with some symmetry and geometry of the situation. But nonetheless, it's a sheet of charge. And we're going to look at little point at an axis and measure a position outward from it. This is a three-dimensional view of a circular sheet. So imagine a circle turned on its side, and we're looking at a point out from the center of that to figure out what the electric field might be at that point. Now, electric field of this sheet is nothing right now until we give it a surface charge density, and that's defined as sigma. Now, sort of like the line of charge that had a linear charge density, this surface charge density is denoted by the Greek letter sigma, and that's equal to the total charge divided by the area of that circle. So we should give some dimensions to it. I'll give a indication that this is the radius, and if that's the radius, then the sigma is the surface area of that circle, which is pi r squared. So I'm going to use a pi r squared. That gives you an idea what sigma is going to be, and we're going to come back to that shortly. All right, so if we're looking at the electric field here due to a bunch of positive charge distributed uniformly on this disk or on the surface, we're going to have to start looking at little pieces of that sigma. Now, I did define an R value here. I'm going to go ahead and change that, though, to a large R, meaning that the whole disk has a size big R, because in just a moment, we're going to start thinking about a little segment here, a little piece of this disk, and that's going to be our little piece of the overall charge dq. Okay, so when we think about that little dq, it is positioned a distance r away. And that brings us to our first step of the problem solving process. What is dq going to be? All right, now dq is located at a position right here on the disk. It could be over here, anywhere on this disk. It could be on the outer edge. It could be up here, our little piece of charge. We're trying to figure out the electric field due to that. If I make a little indication here of a triangle, then that little dq will have a electric field contribution dE at that point. Trying to keep things very similar to the previous problem. So instead of a ring, we've got a disk now. Now that dq, to figure out what it is, it's at this particular position here. However, there are a whole bunch of other charges at a similar position around the center of that circle. And you see, all of those around the center, very much like the ring of charge, are at the same distance away from our location here. Now let's go ahead and define a location. Let's say this thing is a distance of x away from the center. That's what we're looking at. So we got an r up to the dq and x out to the electric field. But any point around in the circle here, I just kind of connect the dots, all those points are at the same distance away from our location. Now, we could look at a dq up here, which would similarly have the same electric field strength as any of these points around. So you see there are rings and rings around the center of this disk where the electric field intensity is the same from a little piece dq of any point on those rings. So instead of calling my dq a little square here, let's just make it an infinitesimally thin ring. And that's what we're going to define as dq. Right? Because it would all have the same amount of electric field intensity. And we will get to some symmetry later on where some components cancel. But let's just say here that all of them, similarly to the other scenarios, will have an x direction component of their electric field that is going to be a non-zero value. You can imagine like the bottom of this would have a crisscrossing effect here, and those y components would cancel. We're going to get to that shortly. But let's just take that ring as our dq. So what would that dq equal then? Well, of that ring, how much of it is taking up how much of that ring is okay. That dq is taking up how much of the overall ring? Well, if we compare Q over area, the total charge given to this thing, you could say it's got a sigma, but an overall Q value, okay? So that overall charge of the disk divided by the area is pi big R squared. Well, what would the area of this little ring be? Well, if you look at it, it's a circle. And it's a circle with a very, very thin inner circle to it. So if you want to think about it like this, it's kind of like an inner circle and an outer circle, where the little width there is a tiny, tiny small distance dr. So what would the area be? It would be 2 pi r, would be the circumference of that circle, times a little tiny width, dr. All right. Now you could say, what if you've got an area, then what would be sometimes people compare these two numbers here, and while it does have a little meaning here, the little dA, little piece of area for an area of pi r squared would be 2 pi r dr, and that does happen to be what we have up here. So that might be a way for you to remember this. But more specifically, it's a ring, a ring with circumference 2 pi r with a very, very, very thin thickness of length dr. And that's going to be important here because as we go out further and further and further, that ring becomes further and further away from E. So that from the electric field point here. So as those DQs get further and further away from the center, they will have a changing R value. And the thickness, the little dr in there, is in that direction. So this is very appropriate. As we get further and further away from the center, the electric field due to each ring of DQ will be different. And further out from the center is along the R. R is what's changing here. And that's what we want to be reflected in our future integral. All right, so we have here sigma is equal to dq over 2 pi r dr. Therefore, dq, actually I want to get rid of this ring first. There we go. dq will be equal to sigma times 2 pi r dr. Sigma 2 pi r dr. Second step, what is this R naught? Remember that is the distance between the electric field and dq. And notice that's why we picked this ring, because every point around here in this ring on the disk is at a distance R naught. And that's equal to x squared plus r squared square root. Okay, so there we have our R naught, square root of x squared plus r squared. Third, is there any symmetry to this that where we're going to have some canceling components? Sure enough, if we consider a little piece of the ring down here and a little piece of the ring up here, they're going to have crisscrossing components. And with the one from down here, there it is. And their y components will cancel, their x components will add. Well, what about a little piece of this ring over here versus a little piece over here? Well, those components will have, or those electric field contributions dE will be coming in sort of like this. There's one kind of going into the screen there, and here this one's coming to the right and out of the screen that way. Well, they're going to have some, call it z direction components out that way, and they'll crisscross and cancel. But in addition, they'll also have x components as well. So those we can call it, if this is the z direction out here and this is the y direction, we might say that, getting rid of all that because that it's going to get a little confusing with the rest of our diagram. All in all, we can say that sum of our forces in the y direction equals 0, and the sum of the forces in the z direction also equals 0. Very similar to the ring scenario from our last episode, and all that's due to symmetry, or superposition of charge. And next, we're ready to set it up, I think. Let's see. Our x component, we're going to have to find the electric field for that. And this is where we're bringing in our friend up top there. 4 pi epsilon naught times dq, and our dq is listed up there, sigma times 2 pi r dr, divided by r squared, and that would be x squared plus r squared. All right, we also need the x component, so let me go ahead and define a theta here. There's our theta, and the x component would be the adjacent side. If we make a little triangle with that, there's a little triangle, right? And the adjacent side of that triangle would be the cosine component of theta. The theta here is equal to the theta over here. We've got those bisecting lines. We have congruent angles. So if this is theta, then the cosine of theta would be adjacent divided by hypotenuse. Therefore, we're going to multiply this by cosine theta. I'll just write that out there. Cosine theta is our adjacent side divided by hypotenuse. And that's what we're going to multiply over here. So electric field times cosine of theta, x over root x squared plus r squared. And that will be all in the x direction. Okay, all right. Here's our little change, our little d, our dr. I'm going to first combine some similar terms and pull out some constants. Up here, up top, I'm going to go ahead and erase that one in favor of sigma and friends. And we're going to have a 2 pi r sigma. We also have an x up top. That x is a constant. And now what's left? We've got, ooh, acted a little hastily. Don't be hasty. Thank you, Pippin. Back. R needs to come out with its friends. Okay, so we're going to have a 2 pi sigma, and an x up there in the numerator. And inside the integral, we're going to have an r dr divided by, plug these two in together, similar terms, we've got an x squared plus r squared to the 3/2 power. There we go. All right, so we have constants out front. Looks like we can divide out that 2 pi divided by 4 pi leaves us a little 2 there. But even with that, we're ready to integrate both sides. This is going to give us our total electric field in the x direction. And what do we integrate this from? What are our bounds going to look like? Well, we're going to sum this up from, an r of 0, where we're going to have a very, very zero radius ring, to larger ring, larger ring, larger ring. So we're going from a radius of 0 to capital R. 0 to capital R. Okay. And that should give us our entire electric field. This becomes a calculus problem now, a math problem. And we're going to take that on. Next step. Got our constants out front, sigma x divided by 2 epsilon naught times. Ooh, okay, what's going to go on here? Well, we've got a number to the, like in the denominator, we've got this x squared plus r squared, and we're taking this in terms of dr. We've got a dr here. So what if we try to make this our u? We're going to do some u substitution. Make u equal to x squared plus r squared. And so if we substitute u in for x squared plus r squared, we're going to have to substitute a value in for dr. And you're going to see why this works here in a moment. When we take the derivative of both sides, derivative of x squared, that's a constant 0. And then the derivative of r squared would be 2r dr. And that means dr is equal to 2r, is equal to du divided by 2r. And I'll go ahead and slide that down a bit. All right, du divided by 2r. Now we can substitute those into our expression. Let's see what happens here. We're going to have an r, and then dr is du divided by 2r. And when we substitute in x squared plus r squared is equal to u, we end up with a u to the 3/2 power. All right. Now, two ways to do this. We could just kind of leave the bounds out for a little bit, and when we get our result, we can substitute x squared plus r squared back in for u. But this one's just kind of easy enough. I'm going to plug in an r, capital R for this r, and a 0, and that'll give us our two bounds. So when I plug in a capital R, the top bound is x squared plus capital R squared, and the bottom bound, that's a little difficult to see. So when we plug in the capital R here, we'd end up with a top bound of x squared plus capital R squared. When we plug in a 0 for r, our bottom bound would be just x squared. All right, so now we see why the du substitution is going to work, because we do have an r in the numerator and an r in the denominator, and they cancel. And we're left with just du over 2 u to the 3/2. I'm ready to continue our integral here. I'm just going to rewrite this. Got sigma x. I'm going to go ahead and pull out that 2 to make this 4 epsilon naught. And now to rewrite the integral, I'm going to make this u to the negative 3/2 du. And that, of course, is really easy to work with. X squared, and we get a x squared plus r squared up there. Okay, let's keep those. After this, we're going to have a sigma x over 4 epsilon naught. And the integral of u to the 3/2, we're going to add 1 to that power, which would give us u to the negative 1/2 divided by negative 1/2. All right, looks a little funky there, but it's pretty easy integral. Get down and continue on. All right, sigma x 4 epsilon naught. And this divided by negative 1/2 gives us a negative 2 up top. 1 divided by negative 1/2 is negative 2 times 1 over square root of u. U to the negative 1/2 is square root of u. Okay. Now we're ready to apply our bounds from x squared to x squared plus r squared. I'll bring that down to the next line. Negative 2 over 4 is just negative 1. So we have negative sigma x over 2 epsilon naught. and we're going to throw in our u. So negative the square root of x squared plus r squared minus 1 over square root of x squared. All right, at this point, I'm gonna go ahead and distribute this little negative here. I'm gonna distribute that negative to both sides, and that'll give us a positive there, negative there, and a positive there. Okay. We have a 1 over square root of x squared. Okay, that's same as 1 over x. And now if I also distribute this x to the top in the numerator over here and distribute that x like that, so in essence I could distribute a negative x to both sides. Just clean all that up. We'd end up with a sigma over 2 epsilon naught times, well, let's do this positive term first. X divided by x is 1 minus x divided by square root of x squared plus r squared. You should really work through this math yourself, because me waving my little pen here isn't going to do as well as you disciplining, getting better in your discipline and working through it. So that's going to be awesome for you if you can do that. Okay, and I think this is my most generic problem or generic solution as I can get. Again, this is for that disk. We're looking at a point right out here. This disk has a dimension large r, and we're at a distance x away. And that's our electric field at this point. All right, looks kind of funky again, but we're going to now consider some limits. In this limit, what we're going to do here is we're going to kind of like the big line of charge. We're going to get really close to that surface, really close, such that x is much less than the dimension r. And when we do get very close to something like this, it does become like an infinite sheet. So for that infinitely large sheet of charge, pause for emphasis. All right, this is when r is much greater than x. So let's consider a solution to that. If r is much greater than x, what's going to happen here? Well, we'll have, looking at our expression, we'll have a relatively small number up top. And down below, if r is much greater than x, then in this square root term down here, the r is going to overpower the x. So think if r is 100 and x is 1, 100 squared is 10,000. When we add 1 squared to that, we get 10,001. So is the square root of 10,000 and the square root of 10,001, is that number any different? No, it's not. And now put on top of that, if x is 1, then this term becomes 1 divided by the square root of 10,000, or 1 divided by 100. Well, 1 divided by 100 is 0.99. But this is an infinite sheet of charge. R isn't just 100, it's like millions large. Well, x is 1. So what is 1 divided by a million? 1 million. It's an even smaller number. So as r gets much bigger than x, when we approach an infinite sheet of charge, or in other words, when we get really close to that sheet, what is the electric field like? This whole term here approaches 0 as we get closer and closer in. All right, this becomes a 1 divided by a very large number, and we get a 0. So what's the solution look like? It just turns into this, the electric field of near an infinite, near a very close to a sheet of charge. In other words, that infinite sheet of charge electric field has nothing to do with the distance. It is only the electric charge the surface charge density divided by 2 times a constant. There's no x value here. We should note, though, it would be in the direction of the distance away. So this is a vector here. It's a position away from there. The electric field would be going outwards. If this were a positive sigma, it would be going inward if it were a negative sigma. And that is our illustrious solution. And it's going to tell us a lot about some very real devices coming up. For example, a capacitor is an electronic component, and at its essence, it is 2 sheets of charge that are separated, but they're not separated by much distance at all. So we could say they're 2 sheets of charge, and when we're looking at objects that are in between them, for a capacitor, you wouldn't really look at that, but you can create some really awesome electric fields in between 2 sheets of charge that are very constant. And scientists like particle accelerator genius people, they're going to use those electric fields between sheets of charge to do some pretty awesome stuff. And you guys are going to see some of those things that happen later in this course. So let me just sum up with considering, what if we do have 2 very large sheets of charge that are rather close together? All right. And now usually what happens here is if this were a capacitor and this is a symbol for a battery or like a D cell or something like that, you might hook up this side to the positive side of the battery and this side to the negative. All right, and that produces a sheet of positive charge over here. And we have a sheet of negative charge over here. And the thing is, because they're connected, same battery here, generally when you got 2 sheets of charge like this, they have an equal surface charge density, but opposite sign. So an equal amount, but opposite. So therefore, what would the electric field here or here or here, kind of anywhere near the middle of those sheets of charge, what would the total electric field be? Well, remember, if we've got an infinite sheet of charge, just a pretty close distance away, the electric field is sigma over 2 epsilon naught. Well, here we've got the electric field lines going from the positive toward the negative. All right. So the electric field at this point due to the positive plate is that way, and the electric field due to the negative plate is also that way, and they both have a magnitude of sigma over 2 epsilon naught. If we drew a little electric field diagram here, we'd have the electric field from the positive sigma and the electric field from the negative sigma both going in the same direction from this perspective. So we add that up in between these 2 plates, we'd have a sigma over 2 epsilon naught plus a sigma over 2 epsilon naught. And you might be saying, why isn't this one negative? Because they're both in the same direction. Look at the perspective here. Field lines go from positive toward negative. So on any point in between these plates, the field lines are very, very uniform. All right, and we're just going to add their absolute values, add their magnitudes together, and you get 2 sigma over 2 epsilon naught, where the electric field in between 2 charge plates of equal surface charge density is just sigma over epsilon naught. And that's something that you can carry forward from here. Come back to this lesson if you need a little reminder on it. But I have good news. In our next couple lessons, I'm going to introduce something called electric flux. And from that comes Gauss's law. And this is an amazing thing. It turns all these electric field calculations for many of the objects we've been studying here, especially for that line of charge and the surface charge. It makes this whole problem-solving process extremely easy when you consider how Gauss looked at it. So it's kind of akin to when you're learning about limits in calculus. You learn how to find the derivative using limits. And then all of a sudden, the teacher introduces the power rule. And you're like, oh my goodness, why didn't we not use this just a moment ago? Because power rule is like, boom, boom, boom. You move one number, you put it in the front, there's a coefficient, and you reduce the exponent, and bam, you got the answer out of it. You're like, all right, pulling my hair out before with those limits. But now, probably been pulling your hair out with these electric field calculations. When you see Gauss's law, it's going to be a snap. So we'll see you in a few episodes. Hope this made it easier. Hope you learned something.